here in Saudi Arabia. Okay. Prior to joining the International Technical College, he was working in Higher Institute for Water and Power Technologies, HIWPT, and Higher Institute for Paper and Industrial Technologies, HIPIT. And he worked as a senior electrical design site inspection engineer of the National Agriculture Company in Alvis in Saudi Arabia. He graduated from Adamson University in 2004 with a degree of Bachelor in Electrical Engineering and a degree of Master in Electrical Engineering in 2006 after successfully defending his research. His research work was in power systems, especially system losses of distribution utility. He had worked both as an electrical design engineer and site inspection engineer in various consulting firms in the country, in several companies. He had taught electrical engineering in several reputable institutions in the country, such as Adamson University, Mapwa Institute of Technology, Asia Pacific College, and St. Louis University. Wish you will enjoy the talk today from Mr. Dave, and hope it will be very useful. Mr. Dave?
Yep. Thank you so much, Mr. Ibrahim, for that wonderful introduction.
Most welcome.
Okay, so our topic for tonight is about the voltage drop calculations based on SBC 401, the Saudi Building Code 401, and also the requirements of the National Electrical Code. So we come up with this topic for the reason that this is an most applicable.
Just Mr. Dave, 1 minute. Somebody is saying, I think.
I can hear. Yeah.
Yeah, he said I cannot hear. Just make the speaker on. Just look for the speaker and make it on.
Yeah. Just look for the speaker.
Can you hear now, Alvin?
It's okay now. Everybody can hear me now.
Yeah, please confirm if anyone has any issue with the mic, please, or the speaker, please.
Yeah, before we start.
Alvin, can you hear now?
Okay. Elvin, Rodel, Camille, Hussein. Okay, I think oh, you replied already. Mine is good.
Okay.
That's too much static. I don't know where's the static coming from. Is it normal, Mr. Ibrahim, to have those static?
Yeah, for me it's very clean. For me it's very clean, and it's very...
Okay. Okay. So loud and clear. Okay. So shall I proceed, Mr. Ibrahim?
Yeah, please.
Okay. So someone asked us about the requirements for the voltage drop calculations, because when you read the book, there are so many things that mention about the voltage drop calculations. Other publications, they are using different methods, and the others are also different. So we come up with this kind of topic to clarify these issues regarding the voltage drop calculations based on the Saudi Building Code 401, or the electrical code of the Saudi, and also the American standard, which is the National Electrical Code. So this topic would be, we believe that it will be applicable for, of course, the designers, the engineers. If you are designing something, so knowing the requirements would be helpful for you. For the students in your thesis or in your research, it will be very helpful. To the site engineers also, when you are installing something, so these voltage drop calculations will be very helpful for you guys. And of course, to the educators, to the academe, because SBC 401 is now a requirement for everybody. So we have to teach this one to the Saudis, and I think they will standardize everything now starting this year. So they will have this SBC 401 or the Saudi Building Code as standard for all. All right. So we have 1 hour, so 55 minutes now. So the objectives would be, first we will know the concept of the voltage drop. We will have some short introduction to that. And we will know the importance of voltage drop. Can you please mute Mr. Said? Yeah. Okay. Welcome, sir. Can you please mute your microphone? Yeah, thank you. And we will also derive the formulas in calculating the voltage drop. So first we will have the approximate method, which is commonly used. And now also most commonly used is the simplified approximate method. And then we will also use the exact method from IEEE. And all of this, actually, we will have the both single phase and the three-phase system. And we will also follow the SBC 401 requirements, the Saudi Building Code requirements in calculating the voltage drop. And we will follow the NEC requirement in calculating the voltage drop. And last, we will have also solve problems involving voltage drops to clarify everything, so that we will have an example. Okay, so the concept for the voltage drop is very simple in terms of the conductor has its own internal impedance. So we all know this concept that whenever a conductor has its area, its length, the type of the conductor, metal, so all of this will have its resistance and also will have its inductance. So if you combine those two, so inductance, of course, when you supply an AC source, that inductance with the frequency, it will become a active component called the reactance. So if you combine the resistance and the reactance, you will have the impedance. Okay. So voltage drop is present whenever current flows through the cable. So we have the current here, and then we have the impedance here. So the current multiplied by the impedance, we will have the value of your voltage drop, the current multiplied the impedance. And now we have the length. So why do we have length? So we all know that for every length, entire length of your cable or your conductor, you have all those resistance and reactance present on it. So for example, you measure your cable for every meter. So every meter of its length will have its resistance and will have its reactance also. Relatively, the most dominant component is the resistance. So reactance somehow is a smaller part. However, for some exact calculations, we will also consider the reactance. So knowing that formula, that the voltage drop is the current multiplied the impedance and the length, so we will have the factors that will affect our voltage drop in the system. So, of course, the number one factor is the current flowing. The higher the current, higher the voltage drop. We all know that one. So, and number two, it's also directly proportional. Number two will be your impedance of the conductor. So the higher the impedance, higher the voltage drop. So that is why if you have your if you want to decrease your voltage drop in the system, you will just look at into these two factors. Number one is the current flowing, and number two is the impedance of the conductor. So for the building, we don't have much control to reduce the current flow, because the only way to do that for a constant power is to increase the voltage. But we cannot do that in the building or the low voltage application. So the only thing that we can touch in order to reduce our voltage drop is the impedance of the conductor. So in order to reduce the impedance, of course, our most common method is to increase the size. So we all know when you increase the size or the cross-sectional area of your conductor, you will have a decrease in resistance of the conductor. So let's say, for example, in your system, the supply voltage or the sending voltage is 277 volts AC. Okay, and then the voltage drop in one line will yield to, let's say, 10 volts. And then the other return line on the neutral line will give us the 10 volts. So we can say that the receiving voltage at the load would be the sum of its total voltage drop. So the receiving voltage across the load will only be around 257 volts. So if the voltage is still on that acceptable range, that's okay. No problem for the system. However, if the voltage drop will increase so much, affecting the voltage across the load, that will be the problem. So we have to make some solutions how to reduce the voltage drop. One of that is, as I mentioned, to consider your impedance in the conductor to reduce it. Okay, so that will come to us the importance of your voltage drop. Why do we need to calculate the voltage drop? So consider this load or the motor. Okay, try moving closer to your microphone. All right. So consider this load to the motor. So we have, let's say, a motor that is rated at 460 volts, three-phase. The supply is also 460. Let's say that is the supply voltage, and the rated voltage of the motor is also 460 volts. So what will happen if, for example, the voltage drop across to the line from that source going to the load will be amounting to 50 volts. So that would mean the voltage given to the motor will be only 410 volts. So what will happen to the motor? Of course, we all know when you supply over voltage to the motor, it will burn. What will happen to the motor if he will receive under voltage? So if he will receive under voltage, it's still the same effect. Because of the torque of the motor, he will try to achieve that, but in return, he will take more amperes. So if he will take more amperes, he will heat up and the windings will burn also. So that is why calculating the voltage drop is important to ensure proper operation of the equipment. Same thing with other equipment. If you are giving them lower voltage, they will not operate properly. So we all know also that the voltage drops are part of your losses. So your losses in the entire system would be if it is higher, so therefore the efficiency of your system is not good. So we don't want those losses in our system. So that's why calculating the voltage drop will help us determine if our system is efficient or not efficient. So I think those are two major reasons why we need to calculate the voltage drop in a system. Okay, now let's go to the methods of calculating the voltage drop. So there are different approach in doing the voltage drop calculations. Let's all deal with those. Hello? Yeah. Mr. Rami, are you okay? Okay, so if you have questions, gentlemen, you can you can type it in the chat, and I will find some time to address them one by one. Okay, so for the voltage drop formula, first let's do the approximate method. So for the approximate method, let's start with the single phase. Okay, for the single phase two-wire system, when you say single phase two-wire system, we have line, and then we have the return path would be the neutral. Okay, can I close this one first, participants? Okay, so line and then the neutral. So that's your single phase two-wire system. So in this case, what's that coming? Mr. Ibrahim, are you there?
Yes, I'm with you.
Yeah, the slides are having some technical
Mr.
problems.
Rami, can you mute? Can you mute your microphone? Just click on the mic, Mr. Rami, to mute.
Okay.
Now it's back.
The arrow just suddenly is out to click down, Mr. Ibrahim. For the next page.
Can you try again?
I will upload again. Okay. Okay, now it's coming. So if you supply from the source going to the load, so we have the line over there, right? So this line will have its impedance. As I've told you, the dominant part in the impedance is the resistance. So this impedance is also present to both line and the neutral conductor. So the current will flow from the line, goes all the way to the load, and then return back to the neutral. So if you will consider the voltage drop across the line, so you will have the current multiply the impedance across that line. And then the same current will flow to the neutral. So therefore, that current, same current, multiplied by that impedance of the neutral will also give a voltage drop. So therefore, we are computing for the voltage drop in single phase two-wire system as 2 times the current times the impedance times the length. So don't forget the 2 if you have the single phase two-wire system, because 2 would mean that is the complete return path, round trip. We call it round trip from line.
Mr. Dave, can you reshare the file?
It's not, you cannot see it from there?
No.
Okay. Let me just share the file.
Okay, now it's fine.
No, just 1 minute. It's uploading now. My part. Okay. I'll just find that page. Okay, so we are here now. So the voltage drop would be 2 times the current times the impedance times the length. The length from the source going to the load. Okay, so one-way length from the source going to the load. And don't forget the times 2. The times 2 will always mean that it's a round trip path for the current, because the current will also flow to the neutral in a single phase 2-wire system. So if you expand more of this impedance, so you will have that effective impedance would mean the resistance times the power factor plus the reactance times your sine of your phase angle. So it's still the same. So we will just expand that impedance. So this is our general formula for approximate method for single phase.
Mr. Farouk, please can you mute your mic? Just click on the mic to mute.
Welcome, Mr. Farouk.
Thank you. Thank you, Mr. Dave.
Welcome, boss.
Thank you.
Welcome to Jeddah again.
Thank you.
Mr. Farouk, please can you mute? Can you mute the mic?
Yes, yes.
Okay. So where the current, of course, I is the current flowing in the circuit, and then your Z will be your resistance, reactance, or impedance. The impedance. This impedance is in terms of per 1,000 foot or meters. So it depends on the standard or the catalog that you are using. And then the one-way length would be the distance. It's either in terms of foot or the meter. And then, of course, the power factor of the system or the load. So let's have an example for this formula. What would be the voltage drop for a 12 ampere load powered by 120 volts AC, single phase, 60 hertz, 4 mm squared conductors, and a distance of 100 feet? Assume power factor 0.85, and that power factor will give us an effective resistance or impedance of the cable 1.7 ohms per 1,000 foot. So it's already given, the impedance is already given. So in this case, we will not search anymore for the resistance and the reactance of the cable because the effective impedance is already given. So that is the diagram of it. So we have 120 volts AC, and then the current flowing is 12 amperes. The conductor size is 4 mm squared. So the impedance effective is 1.7 ohms per 1,000 feet, 1,000 foot. So in order to do that, just have your voltage drop formula, 2 times the current times the impedance times the length. Why we have 2? Of course, again, this is a round trip path for a single phase system. One line from here, and then the current will come to the neutral, so we have that too. So just apply those values. We have 2 times 12 amperes times 1.7 ohms per 1,000 foot times 100. Okay? So we can have that, cancel the unit for the foot. So we will have around 4.08 volts. Now let's proceed with a single phase split phase 3-wire. So when you say split phase 3-wire, we have 2 lines, line 1 and line 2, and then we have the neutral. The return is the neutral. However, in the neutral, since this is balance, when you say balance, no current is flowing in the neutral conductor. So there is no current that will flow in that neutral conductor. So therefore, if there is no current flowing in this neutral conductor, the formula to be used will still be the same as your single phase 2-wire system. But in this case, not line and then neutral. It's going to be line and then going to the line 2. So where do we usually use this system, line 1 and line 2? So in your house sometimes when you check the voltage. So the one before the old system given by SEC. So we have line to line 220, and then the line neutral is 120. So we have those line system. So this is still a single phase system. So in this case, if you would like to compute for the voltage drop, the same formula you're going to use, 2 times the current times the impedance times the length. So why we did not consider the neutral? Simply because there is no current flowing in the neutral. Okay? So if you expand again the impedance, you will have the resistance, and then you have the reactance component, and then multiplied by the length. Okay, so we will have an example for that later. Now, still on the approximate method, now let's go for the 3-phase, 3 or 4-wire system. This formula doesn't matter if your system is 3 or 4-wire, but usually what you're using here is the 4-wire system for the building. So that would mean you have your line 1 or line A, B, C. So line 1, line 2, and line 3. Okay. So if we have this line A, line B, and line C connected in Y,
Mr. Dave, just 1 minute.
Yes, Mr. Ibrahim?
Yeah, Mr. Ashraf, please click on the mic to mute, if you don't mind. Mr.
I don't know, can you hear me? Can you hear me? It's working now.
Yes, we can hear you, but can you...
Welcome.
Can you just click on the mic to mute?
Okay, thank you, Mr. Ashraf. Okay, so for a 3-phase system, the formula in calculating the voltage drop would be effective if you have a system that is balanced. So what do you mean by balanced system? So when you have a balanced system, the current flowing at phase A and the current flowing at phase B and the current flowing at phase C will come all together to return to the neutral as IN. So this neutral current is equivalent to 0. So there is no current flowing at the neutral. So how is that possible? So later I will discuss that one. So if this is balanced, so therefore, in taking the formula, that would mean the phase A and the neutral. So that would mean our formula is still in terms of line and neutral. However, if you are in 3-phase, you have to convert it into line to line. So if you would like to convert line to line from line to neutral, so you have to add square root of 3, or that is equivalent to 1.732. So the formula in getting the voltage drop for a 3-phase would be square root of 3 times the current times the impedance times the length. And if you will expand that more, for the impedance, you will have the R power factor multiplied by the resistance times the sine of your phase angle. So what do you mean by balance? So why we don't have current in the neutral? So just remember our balanced 3-phase system. So if you have a 3-phase 4-wire system, this is the most common system that we are using in the building. So why we use this one? So that you have a flexibility to utilize both the single-phase load and a 3-phase load. So this is the most commonly used for the building. So that if you have a single-phase and 3-phase in a building, you can utilize those voltages. So for balanced 3-phase, the line currents at phase A, phase B, and phase C, they have all equal magnitude. So when you say have equal magnitude, that would mean If this is 12 amperes, 12 amperes, 12 amperes for IA, IB, and IC. And their angle.
We lost the slide.
Oh, slide was lost. What's that coming? Okay, Mr. Brahim, can I upload it again?
Yes, you can. Yes, you can.
What is that?
Now everything is fine. We can see the slide. We can see you.
Oh, you can still see the slides now? Okay.
Yes.
All right. So they have the same magnitude, and they are displaced at an angle of 120 degrees. So let's say, for example, the phase A current is at 0 degrees. So the other would mean IB would mean at angle of 120 degrees, and the other one would be at an angle of 240 degrees. So if you will add those, if you will take the phasor sum of those line currents IA, IB, and IC, it would be equal to the neutral current flowing in the neutral. So if you will add at an angle of 120 degrees, it would be equivalent to 0. So you can try that in the calculator if you have that one in your beside you. So that is why when we take the formula for the three-phase, this is only one line and then the neutral, but we don't consider the round trip for the neutral. So we don't have the factor of 2. And then the line and neutral, we just transfer it to line and line, so just like this one. So the formula for three-phase is square root of 3 multiplied by the current and the impedance and then the line. So the resulting voltage drop here is between line to line. Okay? Okay, let's have an example. So what would be the voltage drop for a 30 ampere load powered by 400 volts AC three-phase 60 supply with 3 core by 6 mm² XLPE PVC sheeted conductors? So XLPE means cross-linked polyethylene and PVC is your polyvinyl chloride. So the distance is 120 meters. Assume power factor of the load is 0.85. So usually the power factor, if you are designing, you don't want your power factor to be so low, of course. You will not design a system that is not efficient. So the minimum that you can have is 0.85. If you get more than that, that is good for the system. You will have a lesser voltage drop. So that is why usually what we do in the design, we always use the power factor as 0.85. So in getting that 0.85 power factor, you can get the phase angle, which is equivalent to 31.79 degrees. When you say phase angle, this is the angle between your voltage and the current, between the voltage and the current. So if you don't know the phasor of this, so this will be the angle between them. And you can take also the sine of that angle, and that would mean this is equivalent to 0.53. And next, after getting that phase angle, the cosine phase angle and the sine of your phase angle, you can now visit some catalog. Thank you. You can now hear me. Okay. So any catalog you can use. So in this case, I'm using the Saudi Cable Company catalog. However, in using this catalog, you have to be very careful on the type of the cable. So in this case, I'm using 3-core, the multi-core XLPE PVC conductor cable. So there are so many pages that you have to check properly. So this is XLPE insulated and PVC sheeted, which is equivalent to this. And then the multi-core, 3 cores, so this is 3 and 4 core. Because the other part of it, you will find it single core, and some others have different insulation. So you have to be very careful on that. So in this catalog, you can find the conductor resistance. The conductor resistance is in terms of ohm per kilometer. So I'd like you to take note of this. So ohm per kilometer. Oh, it's too big. Okay. So we have here ohm per kilometer unit. All right. So if you will choose the 6 mm squared, you can find the 3.93 ohm per kilometer resistance. And then under the reactance, just choose the 3 core. So you will have that ohm per kilometer also, which is equivalent to 0.1109 ohm per kilometer. As you can see, relatively, 3.93 is way bigger than 0.1109. So this is what I mentioned before, that the dominant factor in that impedance is the resistance compared to the reactance. Okay, so knowing that 3.93 and 0.1109, we can now compute for the voltage drop using our approximate method. So the given in that problem, we have the current 30 amperes. The length is 120 meters. If I'm going to convert that in kilometers, so that would mean that is 0.12 kilometers, just divided by 1,000. And then the resistance, as we found in the Saudi cable company catalog, this is 3.93 ohms per kilometer. And the reactance is 0.1109 ohm per kilometer. And then the power factor is given there, 0.85. And then the phase angle difference. And we can solve for the sine of the phase angle difference. Or we call it reactive power factor, 0.53. So the solution, of course, you know the voltage drop formula. So that is square root of 3 times the current times your resistance multiplied by the cosine of the power factor, and then the reactance multiplied by the reactive power factor. You will get this part as your effective impedance. So just supply the values. Yes, Engineer Elvin. Yes, sir. Can you hear me? Yeah. Can you mute your microphone, please? Okay. So square root of 3 times the current is 30 amperes. And then there's a resistance per ohm per kilometer, that is 3.93 multiplied by the power factor, which is 0.85. Okay? So, and then the reactance, 0.1109 multiplied by the reactive power factor. Engineer Elvin. Okay. Cannot hear me. Okay, so after that, you multiply this. You have to multiply it by the entire length so that will cancel that kilometer, ohm per kilometer. So you will have square root of 3 times 30. So this is that component. And if you simplify all of this part, you will get this value, 4079. So if you simplify further, you will get the value of the voltage drop, which is equivalent to 21.195 volts. Okay? So that is how you compute for the voltage drop using the three-phase approximate method. Now, let's go to the other method of calculating your voltage drop. So this is called now simplified approximate method. So when you say simplified approximate method, it uses the same formula. However, we will not be taking anymore the resistance and then the reactance. So we remove that one anymore. So what we have, we just need to find the voltage drop per unit ampere, per unit length, or per meter. So actually, this is commonly used in BS 7671 and also commonly used in the, because it's very easy to use actually, so it's commonly used for designing also. However, the only limitation of this, it's only applicable for a specific power factor of the load. And usually, as I've told you, the usual power factor that they're using is 0.85. So if you are designing and you would like to design a much higher power factor, you cannot use this. Method. So you have to use the other approximate method so that you can deal with the power factor that you'd like. So this is the table. This is the table that you're going to find in order to utilize this method, simplified approximate method. So there is a table in the catalog that says millivolt per ampere per meter. Okay, so just find the approximate voltage drop, that one, and then go to the cable type that you would like to use. Okay, so there is a corresponding size of your cable, 1.5 up to the highest that you would like. And then there is a already computed approximate voltage drop. So this voltage drop actually is a replacement of this part of your equation. So you don't have to use square root of 3. You don't have to use R cosine or resistance multiplied by the power factor. You don't have to use anymore this reactance multiplied by the reactive power factor. So you don't have to use them anymore. So all you need to do is change it with this V up. V up is the approximate voltage drop. Where is the square root of 3? No more. So you don't have to do that. Use that square root of 3. So all you need to do is take the voltage drop computed here, multiplied by the current in the circuit, and then the length. So, and then divide it by 1,000. Why do we need to divide it by 1,000? Remember, our voltage drop approximate is in terms of millivolt. So to convert that millivolt into volt, you have to divide it by 1,000. Okay, I hope it's clear. So this is going to be approximate voltage drop. This is in terms of millivolt per ampere per meter. And then the current, full load current in terms of amperes. And then the length, of course, that is the distance from your source going to the load. So you have in terms of meter. Now, let's have a good example. So using the simplified approximate method, what would be the voltage drop for a 30 ampere load powered by 400 volts AC 3-phase 60 Hertz supply with 3 core 6 mm squared XLPE, PVC, and the distance of 120 meters? Assume power factor of the load. So this is the same problem. This is the same problem as what we use in terms of the approximate method, if you remember. So they have the same problem. So why do I use it again? Because I would like to compare the results of the approximate method and the simplified approximate method. So, and then we will use the same problem to compare for the exact method of the IEEE, so that we will see what is the difference between them. All right? Okay. Okay, so there's a question here. Yes. So the catalog says that also. So check the catalog that you are using. the power factor that you will only use in here is limited to 0.85. If you're designing a much higher power factor in a system, you don't have to use this. You have to use the approximate method. All right, Mr. Jericho? Thank you for that question. Okay, so again, the given in the problem, you have the 30 ampere current, and then the approximate voltage drop, 5.9 millivolt per ampere per meter. Where did you get that? You have to get it on the Saudi cable company. We can use other cable company catalogs, so just like Riyadh, Bahara. So there are so many cable catalogs. You can also use the catalog if you have what do you call this one? The NEC. It has a table also for this one. So you can use those catalogs. However, I prefer to use the catalog company in here in Jeddah or here in Saudi Arabia, simply because they are the cable being supplied here, and they are the cable that we are using. So the approximate voltage drop of the 6 mm square, so this is 6 mm square, that one, okay? So this is equivalent to 5.9 millivolt per ampere per meter. Okay, so the length is also 120 meters. So after that, just use this direct formula. Where is the square root of 3? As I told you, there's no more square root of 3. How about for single phase? Am I going to use the 2? No need also. No need to use the 2. As long as you use this approximate voltage drop, that's it. Just direct solution, direct substitution. Okay? So if you apply those values, you will have 5.9 times the current, which is 30, times the length, which is 120, and then divided by 1,000. Don't forget the 1,000. Why is it 1,000? Because this is in terms of millivolts. So you have to convert it into volts, so that the value of the voltage drop will be in terms of volts. So the result is equivalent to voltage drop is 21.24 volts. So if we compare that to the approximate method that we use, the result there is 21.195. And then the result that we had is 21.24. So I think that's okay. It's a very minimal difference. So this is a very negligible already. So that is amounting to 0 point something. Okay, so whichever method that you would like to use for simplified or the approximate, still the same. All right. So now let's proceed. Any questions so far? All right. Thank you, Mr. Ibrahim, for the. Are there any snacks, Mr. Ibrahim? Thank you, Ashraf, for clarifying that. Okay, so now let's go to the exact method. When you say exact method, of course, this is the exact claim. Hello? Mr. Abdullah, yes. How are you, sir? Welcome, sir.
How are you? I just joined the audio. Continue.
Yes, sir. Okay, thank you. So the exact method that I'm referring is appears on two standards of IEEE. So they claim that the approximate voltage drop calculation, there is still that is not being counted on that part. So the two standards are 241, the Gray Book. So the Gray Book was published in 1990, and this is about the electrical power systems in commercial building. So this is a very good reference in designing commercial buildings. And the 141, this is the Red Book. They call it Red Book. So this was published 1993, So this is in terms of electrical power distribution. So if you'd like to design the power distribution in the building, and many things, so you can have a lot of reference in these two books. So they claim that the phasor sum between the supply voltage and the receiver voltage, if you're going to take that sum, okay, and you will find that voltage drop, there is still an error in that calculations. There is still a part that's not being calculated. So therefore, the estimated voltage drop is not only the voltage drop that we have. You remember our approximate method is the current multiplied by the resistance times the power factor, and then the power factor. Okay, so if this is your supply voltage or the sending voltage, this one, from this point up to this point, and this is your receiver voltage from that point up to this point, if you're going to take the phasor sum between the two, or the difference between these two, so what we'll have is the voltage drop. However, if you're going to take the actual phasor sum of the voltage drop and the receiver voltage, this is still not corresponding to the supply or the sending voltage. There is still a very minimal part there that they are claiming, this one, that's still not being counted. So the red book and the gray book, they discuss in detail how to get that very minimal error. Yes, Mr. Ashraf, what's the question? Is the voltage drop calculated referred to each line in a three-phase system? It's a line-to-line, Mr. Ashraf, yes. It's line-to-line. As long as you have this square root of 3, it will be referred as line-to-line. No audio. Mr. Brahim, can you help Mr. Yaya, please? Thank you. So, we have to calculate that part. It might be minimal, but we have to calculate that part if you would like to make our calculations as exact method. Okay, so this is in terms of geometry, the segments of this circle, this dotted line, and then you can get it by using the geometry, your Pythagorean theorem. So I would like to just get the exact formula for that one, because it will give us so much time to deal with geometry. If you would like how they derive with this formula for that error, I can send that to you. Just send me your email address. I will send this to you. Okay? So that error part is equivalent to the sending voltage minus the square root of Bs squared minus the quantity I times your reactance times the power factor minus I times the resistance times your reactive power factor quantity squared. Okay, it's a long formula, but they said this is the exact value. So the voltage drop now would be the estimated, so this one estimated plus the error value. So the estimated value, this one, plus the error value, which is equivalent to this formula. So if we're going to take the actual voltage drop, the exact voltage drop, so it's going to be estimated voltage drop plus the error computed as this formula. Okay? So you remember, using our approximate method or the estimated method, this is the formula, right? The blue part, IR times the power factor, IX times the reactive power factor. And then the green part is the formula for the error. Okay? So that formula for the error. So if you're going to add all of these equations, okay, taking that one, it will yield to this general formula for exact method of calculating the voltage drop. Okay. So this would mean you have sending voltage times the IR cosine of phase angle times the IX times your reactive power factor minus square root of PS squared and so on. Hello? Okay. However, this one is in terms of line and neutral. Okay? So if you have your single phase, you still need to multiply it by 2. If you are computing for the exact formula, multiply it by 2, you have that single phase. And if you have the 3 phase, you have to multiply it by square root of 3. Okay? So let's apply it in a problem so that we will understand it better. So we have here the same problem as we use with the simplified approximate method. It's the same problem. So the first thing we have to do is take the cosine phase angle and the sine phase angle. You know that already. And then after that, we have all the given, the Vs or the sending voltage, or we call it supply voltage, that is 400 volts. And then the current, 30 amperes. The length is 120, 0.12 kilometers. So I converted it already in kilometer. So now the resistance, if you still remember, the resistance that we took from the Saudi cable company, the resistance is 3.93 ohm per kilometer. And then multiplied it by 0.12, that will be your effective resistance for the entire length, which is 0.74716. And then the reactance, multiplied it by that length, you will get the total reactance. Okay? So, taking the solution, remember the formula, this formula here. So, in order to make us simpler, so we will just take these factors. IR cosine phi, we can solve for that one. IR cosine phi. Okay? I hope everybody is following with this. And then IX sine phi, we can take that one too. So that is IX sine of phi. We can take it this voltage. And then I will take also, what is the question? What is the 0.12 kilometer? Okay, so 0.12 kilometer is the length. This one, 120 meters. So if you're going to convert that in kilometers, so that would mean 0.12. Okay? So going back, IX cosine, why do we need that IX? So this is the IX cosine, this factor here. So I'll take that one, IX cosine of phi, that is this voltage. And then the last one is IR sine. So IR sine of phi, so that would mean 30 multiplied by this and this. So you will have this IR sine of phi. And then after that, all you need to do is put them in that equation. Vs is 400. IR cosine of phi, that is the 12.0258. And then the IX sine of phi, this one, minus this one, square root of Vs squared, minus IX cosine phi, minus IR sine of phi. You have to first simplify for this value. Okay, so after you simplify this value and then take the sum and then minus that value, it will give you this voltage drop, 12.3014. But take note, this voltage drop is in terms of line and the neutral. Okay, so if we are going to take it in line, so we have to multiply it by square root of 3. So square root of 3 multiplied by the 12.3014, we will have the value of 21.3066, exact amount or using the exact method for the voltage drop calculations. So if you're going to compare it to the other method that we use, the simplified one is 21.24, and the approximate is 21.195. So pretty close, huh? So which method are we going to use? Simplified, approximate, or the exact method? So the good news is that we are not required. What's the question? Line neutral not multiplied by 2. No, this is three-phase. This is three-phase. This is this formula is in terms of line to neutral, this voltage value. So we have to multiply it by square root of 3 to get for the line-to-line voltage drop. Line to line. Okay. So the good news is that as per the industry requirements, yeah, okay. So the simplest method is okay for Ms. Engineer Rodel. Yeah, me too actually. The simplest, simplified method is okay. So if you are going to follow the standard in designing, so we will have, they accepted, even Aramco actually, they accepted the simplified approximate method or the approximate method. So they are not requiring the exact method. Why? Because of the very minimal error or difference. Okay? So now, I'm losing my time, so let's continue. What is the importance now? We know how to calculate the formula. We know how to calculate the voltage drop. So what are we going to do? So you have to know the rules, of course. What are the rules that you are using, or what we call the permissible voltage drop or the allowable voltage drop? Okay? So if you are designing using the American standard, the National Electrical Code, okay, so they have the new version now, the 2017. So if you are using the standard of the American, so just like the Aramco project, so they are using this one. So this is the requirement. Actually, it's not a requirement, but later we will see what is this information that they are giving. So there are two things that mention about voltage drop. So the first one is about branch circuits. So this is in 210.19a under informational note number 4. It says there, branch circuit as defined, size to prevent voltage drop exceeding 3% at the farthest outlet of power, heating, etc. And the combined total, or the combined on both feeder and branch shall be 5%. Okay, so this one is a little bit confusing. So let's summarize that one. So it says here the branch circuit, you know already the branch circuit, right? This is the final circuit. From the distribution board, it will go to the final load or the load connections. So you have the branch circuit voltage drop should be maximum 3%. Maximum. Okay, so this is what they said. And then the combined, the maximum combined from the feeder source to branch circuit or the farthest outlet, okay, so that should be 5%. Okay, so it's a little confusing. So that would mean if I have 3% there and the total should be 5%, this allows me only a 2% voltage drop for the feeder, right? Okay, so let's see what is the feeder is saying. Let's go to the feeder, 215.2 for the feeders. Informational note number 2. Conductor feeders should be not exceeding 3% again at the farthest outlet, and the maximum total voltage drop should be not exceeding 5%. Oh, it's the same, right? So that would mean The feeder also will have a maximum of 3%. And the combined, I will come to you, Mr. Said, for the 3% of the source voltage. Yeah. The maximum combined would be 5%. Okay? So let's clarify that one. So for example, this is my service. Usually the service is the transformer. Okay? And then I have my sub panel or distribution panel, and then this is the branch circuit, and then this is my load. Okay? It says in 210.19 branch circuit 3% maximum. However, 215.2 also 3% maximum. So simply say 3%, 3%, it should be 6 and not 5, right? But no, that would mean from here up to here, that is only 5%. So you can adjust the feeder, or you can adjust the branch as long as you will not exceed 3% on each. I hope that's clear. Okay? So let's say, for example, this is the question of Mr. Said. So let's say the voltage you measured at the service terminal or the transformer terminal, okay, is 230 volts on the low voltage side, okay? And taking the 5% total, that would mean 5% of that 230. So you are only allowed to have 11.5 volts drop from that transformer going to the branch circuit to the load. Okay? So that would mean don't bring down the voltage to 218.5. So this is what is on saying for the National Electrical Code. So you have to get a 5% maximum voltage drop from the service going to the load. Now, the question is this mandatory? Maybe some of you is answering now. The answer is no, because it's under the informational note only. So NEC clarified that when it says informational note, this is only a guide. Okay, so it's not mandatory. So they are acknowledging the situation, the fact that there is a tolerance of the voltage, of course. However, if it's a requirement for you to have the voltage drop computations, this will be your guide in doing that. Okay? Is that clear? Yes, sir. Thank you. So now let's move to the Saudi Building Code 401. The Saudi Building Code, it says a lot of information that the equipment should not overheat, the equipment should be efficient, the equipment should be like this, and it all boils down to saying that there is a need for voltage drop calculations. However, Saudi Building Code only have this code, 52-5. Is the voltage drop in consumers' installations. So what he says, it is recommended that in practice, the voltage drop between the origin of consumer's installation and the equipment should not be greater than 4% of the nominal voltage of the installation. Other considerations include the startup for the motors, equipment in rush current, if you have a higher, if you would like to compute for the voltage drop during starting, and then the transient voltage and voltage variation due to abnormal operation can be disregarded. So we will remove that one. Okay, now, what he's saying is 4%, but where are we going to take the 4%? Let's take consideration of this statement. Origin of consumer's installation and the equipment. Between the origin of consumer's installation and the equipment. What does it mean? So origin of installation is the point at which electricity is supplied to the consumer or the premises. Okay, so I'll just put that into drawing so that it's clear. So let's say this is your consumer. So we all know that the consumer of electricity, we have three types. Residential consumer, the commercial consumer, and then the industrial consumer. So the point in which the electricity is supplied to this consumer, this is the origin of the consumer installation. So in this case, let's say, for example, this building is being supplied by the SEC transformer. So the service cable is already part of your installation of the consumer. This service cable is already consumer installation. So this will be from this point going to the, of course, it will connect to the distribution board or the switch gear if you have that one, and then the feeder cable going to the distribution board, and then the final branch circuit going to the load or the equipment. So that would mean the 4% should be from this point here up to this point here. That's the 4%. Okay? So that equipment, of course, this is the equipment, the farthest going to the load, either lighting, power, or heating equipment. So the total voltage drop is 4% of the whole installation. So let's have some example that this is, let's say, 230 volts from that transformer. And then 4% of that 230 would only be 220.8 volts. So the voltage across that terminal of that load should not be lower than 220.8. So this is what he's saying, 4%. Okay? Now, which one is much more stricter? Of course, the Saudi Building Code is requiring 4%. The National Electrical Code, 5%. Okay? But the question is Saudi Building Code mandatory? Is it mandatory? The answer is yes. We have to follow that. It should be. Okay? It's not in the informational note. It's written in that code, and it should not be. It should be. So we should follow this one. Okay? So if you are using Saudi Building Code and suddenly your boss will say, why our cables are a little bigger? What standard did you use? Of course, you will say, well, I used the Saudi Building Code, 4%. Strictly followed it. So there's no question about that one anymore. So as long as you say that this is mandatory to follow 4% of the nominal voltage. Okay? So now let's have an example. The last one, Mr. Ibrahim. I hope I still have the time. So this is the last example. Yes.
Yes, go ahead. Go ahead.
Okay. There is a question for Mr. Ashraf. So 9.2, if you will deduct 230 volts, Mr. Ashraf, yes, you are right. That 0.04 multiplied 230, that is 9.2. However, if you deduct that from the source voltage, 230 nominal voltage, it will give us 220.8. Okay? All right. So determine if the cable sizes correspond to the National Electrical Code or the Saudi Building Code 401 to their allowable voltage drop. Okay, so this is the system that we have. So we have there the 2 MVA transformer. And then we have the service feeder cable, C2. So this is 5 sets of 300 millimeters square. And then we have the main distribution panel. And then we have that sub feeder, C4, 16 millimeters square. And then there is an MCC there. And then connecting to the motor, which is the branch, C5, 10 millimeters square. So he's asking if The sizes are okay based on the requirements of the National Electrical Code and the Saudi Building Code. So if you have this kind of problem, the cable sizes are already there. So the method that you're going to use is to get the percent voltage drop and compare it to the requirement of the National Electrical Code. Now, if you still don't have the sizes, you can use the reverse calculation. So you can determine the minimum voltage drop allowed, and then you can get the current, or the current that can flow to the circuit. Okay, so let's do this solution. So because it's requiring us to get the percentage voltage drop in order to check if this is corresponding to the NEC and the Saudi Building Code. So what method am I going to use? Of course, it's already night. I will not use the exact method of IEEE. I will use the simplified method. So I need the voltage drop per ampere per meter. Okay. So I already rearranged it so that I can take all those sizes, 300 mm squared. This is the 300 mm squared. We have 16 mm squared, 16 mm squared, and then 10 mm squared. This is the 10 mm squared. Okay. So again, when you are using the catalog, you have to check properly the type of the cable and what type of it is, a multi-core or single core. Okay, because if you got mistake on that, your calculations will be wrong. So after that, of course, that is the Saudi Cable Company source. You take one by one. So you start with the branch circuit. Yes, Mr. Jericho, you have some question? Okay, so let's start with the branch circuit, which is C5. This is the C5. So this is 4 core by 10 mm squared, XLPE PVC. The length is 55 meters. So just take all those given in the problem. The current is 14.43 amperes. So it's there, 14.43 amperes. And then the length is 55 meters. And then the approximate voltage drop is 3.5 millivolts. So this one. Take it from here. 3.5 millivolt per ampere per meter. Okay. After that, just use the simplified approximate method, voltage drop. So voltage approximate times the current times the length divided by 1000. Again, why is it 1000? That is the millivolt. Okay. So just apply this formula and you will get the voltage drop 2.78 for this length. Okay. So taking the per unit value or the percentage of that, 2.78 divided by your voltage 400. Why is it 400? Because the transformer point, as you can see, 13.8 kilovolt, that's the primary, and this is the secondary, 400 volts. So therefore, all the entire connection here will be 400 volts. So this will be the nominal voltage of this low voltage part of the transformer. So you will take that 2.78 divide 400 multiplied by 100%, and you will get this value, 0.7%. So for that 0.7%, this is the branch. As a requirement of NEC, we should not be more than 3%. Of course, as we can see, this is far way less than our 3% requirement. Okay. Now let's go to the subfeeder C4. So this is your C4. The cable is 16 millimeters squared, and the length is 20 meters. All right. So the current there is 16 amperes. It's there written also. When you are designing, of course, the current that you can have might be different Maybe some of the current that is flowing here to the load is different and flowing to that subfeeder is different because there are some small loads connecting to your MCCs. Okay? So the approximate voltage drop is 2.2 millivolt. So where did we get that? So this is, the cable is 16 millimeters squared. So this is 2.2 millivolt. Okay, are you following? And then after that, you just have to apply the formula. So 2.2 times the 16, the current, and then the length is 20 meters divided by 1,000. You will get the voltage drop for the subfeeder, which is 0.704. Okay? So, and then get the per unit value of that. So that is 0.176%. Now, let's move to the service feeder, C2. So this is the C2. So this is 5 sets. So that means 5 parallel circuit on it, 300 millimeters squared each. So that's too big, right? But of course, we consider that there are some loads connecting on this part. Okay, so we only considered one path of the circuit. All right. So the cable is 5 sets of 300 mm squared. Remember, this is 300, still 300 mm squared. So the voltage approximate is 0.2. This one. So the total current full load for this service feeder is 1,360, and then the length is only 15 meters. All right. So we can calculate for the voltage drop, approximate times the current times the length divided by the 1,000. However, this formula will change a little bit simply because of the 5 sets of the cable. Don't forget that when you have more than one circuit of the cable, or one set, more than one set of the cable, let's say 2 sets, 3 sets. So when you are using this one, please always include that number of sets under the denominator. So this will get the total for all 5 sets. Okay? So that would mean the voltage drop is equivalent to 0.816 volts. And if you take the per unit value of that, and that is equivalent to 0.204%. So taking that, we can have the consideration. So this is the branch circuit. Let's follow first the NEC. So this is less than 3%. We don't have problem for that. The feeder, this one, should not be more than 3% also. So if we add that one, this is also less than 3%. So this is only around 0.37 or 38, 0.38%. So this is also less than 3%. And then the total should be less than 5%. And then following the Saudi building code, which is 4%, this is also less than 4 or 5%. Okay? So any questions regarding these computations? No questions? All right, so no questions. So let's have the summary. So of course, the summary for proper operation efficiency of the system, voltage drop calculations is important. All right, and approximate method for the single phase, you have that 2 times the current times the impedance times the length. Same thing with the split phase, okay? And then for the 3 phase, you have the square root of 3 times the current times the impedance times the length. And then using the simplified approximate method, so this is the simplified. Of course, most of you might have this one all-time favorite also compared to this one. And of course, using the exact method, this is the formula. If you have nothing to do, you just want to compute and compute, you can use this one. You can count all those small decimals, and you are sure that you will have the exact value of your voltage drop. Just remember, if you are using this exact method, okay, multiply 2 for the single phase system. If you have a single phase system, multiply it by 2. This is for the round trip. And then multiply square root of 3 for the 3 phase so that it will be converted into line to line. All right? Now, the requirement for the National Electrical Code, 3% maximum for the branch, 3% maximum for the feeder. However, if you combine them, it should not be more than 5%. Okay? And then the last one is the Saudi Building Code, 4% from the origin of installation going to your farthest load or equipment. Okay? So with that, thank you so much. Can I have a copy of the slides after the lecture? Of course, yes. I'll send it to you, Engineer Russell. So any questions? Mr. Ibrahim?
Yes, with you. Thank you very much, Mr. Dave.
Yep, sir. Safiq, yeah,
If anyone has any question, he can request. I will. I can remove the mute. Dr. Fahad with us, if you want to talk.
Yeah.
Thank you, Mr. Dave, for this great lectures. And actually, we
You're
really
welcome, sir.
knowledge. Hello?
Yes, sir. You're welcome, sir. Yeah.
Thanks. And if there is any question from, our attendants here, please bring your questions.
Yes, sir. Okay, so a lot of questions is about the presentation. Mr. Ibrahim, I will just send the presentation to them, right?
Sure. This is you are free to do.
Yeah. So
And
we will send you the presentation.
Yeah. I will send it to the registered attendees. As I have the list of the the registered attendees.
Okay. So if you are still not registered, please register so that you can give your email address to Engineer Ibrahim Nasar.
Yeah, just a minute.
And then after
I will add the link for registration.
All right. And from there, we can send the presentation. Okay, thank you so much.
Okay, thank you so much. I think we are actually ending this webinars. And thank you, everybody, for attending. And thank you, Mr. Dave. Thanks, Mr. Musa. And thanks also for Engineer Ibrahim. And if there is anything, Engineer Ibrahim, please go ahead. Otherwise, we end up the lecture.
No, thank you, Dr. Fahad. I want to thank all the attendees for joining us today. And we wish to see you in the next seminars.
Thank you so much, Mr. Ibrahim. Thank you so much for all the attendees. Thank you guys for your nice comment. I hope I answered all your questions. And if there's something, you can reach me to my email. If there's something that you'd like to clarify, or you can call me. So thank you again, and have a good evening.
You too. Thanks a lot.
Thank you, Dr. Fahad.
Okay, bye-bye.
Bye-bye.
Bye. Dear all, please just take the link for registration if you want to leave your email and to share the slides later on. Okay, the meeting will end now.